playing around with the idea a little bit, it occurred to me that it would be interesting. It actually occurred to me almost immediately, but it occurred to me that it would be interesting to actually do this. That you can make a program that will give you an infinite series, or an approximation to an infinite series, where all of the components, all of the terms are unit fractions based on Egyptian fractions, right? So it's still based on this, but what it does now, when it decrements the odd numerator and it pulls off the extra one, instead of making it just be 1, it multiplies it by 3, top and bottom. So it's going to have to do it again. And we've removed the fraction reduction from it, so it actually ends up being a simpler algorithm. And I have it, so it's now printing what it has pretty much constantly at every step, along with the string of numerators, because they are not always 1. And it's not entirely it's not simple to predict, at least, which ones will be 1, or how many of them will be 1 when. So that kind of needs to be done. So it does 8 iterations of this currently, which is, for even very small numbers, that outputs quite a lot. So yeah, let's run it. So I have it already queued up over here. So something nice and simple, just some small prime numbers, 5 on 7. There you go. So you can see here it's just decrementing the numerator, 5, to a 4, so you have 4 7ths. And then this would be 1/7, but it's tripling top and bottom, so that it will retain the ability to do that in the next step. And so you're always going to get this trailing 3 as a numerator. But if you do this infinitely many times, if you do this, then that 3 disappears, and all of your numerators end up being 1. So it ends up being an infinite series that sums to your 5/7 or whatever your fraction is, right? So it's convergent, right? So let's see, how did I write this? Please enter 2 integers a and b representing the vulgar fraction a on b, and I will produce a series which converges on that ratio using a technique based on Egyptian fractions. Okay, and I had to fiddle with it a little bit because there were some details that I didn't anticipate, but I think it works now. So if I do something like 2/6, at the end it recognizes that that's 1/3, and here it's not fucking it up. So what it was doing when I gave it an even numerator initially, because it was a bug, I didn't anticipate it. If I gave it an even numerator, it wouldn't work right. This first fraction would be the whole fraction, and then it would have an extra component to it, so it wouldn't sum out correctly. And I think I fixed that, but fuck if I'm testing, this one. I'm not going to just manually try this one. But, I'll manually try, this one. Up to this kind of level, right? So interleaved in here, we have the numerators and then the denominators. So if it's the line that starts with a hyphen, that is the numerator line. They're also systematically shorter. And the line that starts with a 0 or some other number possibly is the denominator line. Yeah. So here, you keep seeing it goes 3, 2, 3, 3, 2, 3, right? So what's happening here is this 2 is getting split off into this 1, 1, and then this 3 is getting split off into a 2 and a 1 that's tripled into another 3. So the 2 turns into these two 1s. This 3 is just preserved. And then this 3 is split off into this 2, 3. And then this 2 is split off into this 1, 1. And then this 3 would be split off into a 2, 3. Right? So that's the progress that makes. But let's do a more interesting fraction. Like, silly thing, 7 on 13. I think this will do it. So you can see here, 7/13 consistently all along it has a triplet of these that just keeps working. So you don't have just 1 3 at the end, you have 3 3s. So there's going to be fractions where I think you could have an arbitrary number of 3s that form at the end of it and to just perpetuate. So you get some interesting dynamics occurring here, right? You can have like basically an infinite number of 3s nested inside your infinite series of 1s. But the infinity of 1s overwhelms the infinity of the 3s. Like, I think that's a possibility. Which that's I wasn't anticipating weird shit like that. Yeah. And then like let's do some actually. This might break it. It might just panic. Some fairly sizable numbers. I think even just double digit stuff like 16 on 25. Yeah, it's panicking. It's like, I'm not going to display all of that. But yeah, you can see, ooh, we get this pocket of 1s here with 2s and 3s occurring. And we're still stuck with, I don't know, that might be the math failing. I'm not sure. Because I don't have it using arbitrary precision. Yeah, here we're getting a 6 and a 24 at the very end. That never goes away, it looks like. That's interesting. But also, so like it clears out this little pocket of 1s, which continues growing. But this end never disappears. And then these 3s that are out front, they grow a pocket of 1s out in front of them. Eventually. Jesus. This is really crazy. There's a lot of interesting shit going on in here that I did not remotely anticipate. Okay, that's some shit. But ultimately, it should yield, ideally, if you run it forever, it should yield an infinite series of unit fractions, which, when you sum them together, will converge on the fraction that you wanted. So here, 16/25 is the fraction that I was looking at. But then there's interesting dynamics inside of there too. Huh. Okay.